So Dr. Thompson is professor at Ohio State University. Before that, he was a Hubble Fellow at UC Berkeley. And then Lyman Spitzer Junior Fellow at Princeton University. Even before that, he was a grad student at the University of Arizona. So he's going to talk about Kozai oscillation in compact objects. So welcome.
All right. Thank you very much for the invitation, and thanks for coming. I will try to make it worth your while. Some of you, I have the distinction of being in a population of people, a lot of whom have worked on Kozai oscillations. So I'm going to try, there will be a few things for experts, but mostly I think everybody will be able to understand it, and obviously if you have a question, please let me know. I want to emphasize that some of the work I'm going to be talking about was done by two Ohio State graduate students, both excellent, Ben Shapi and Joe Antonini, third year and a fourth year student. That line of my talk, so I'll first talk to you a little bit about demographics, some things you need to know to understand what it is I'm going to say. Then I'm going to specifically apply Kozai oscillations to type 1a supernova progenitors. Specifically, I'll be talking about white dwarf mergers in a so-called double degenerate model. But almost everything I say could be extended to the single degenerate model. Then I'm going to talk about other physics and systems. So the first thing you need to know is that stars with mass above 2 solar masses produce massive white dwarfs and neutron stars. So this is the initial final mass relationship from Calroy et al. 2008. And here you see the initial mass and solar masses. So there's the sun, 2 times the sun, 3 times the sun. Then the final mass is here. So a star of about 5 solar masses produces a white dwarf of about 1 solar mass. Solar mass object produces a white dwarf of about half a solar mass. That's the first thing to know. Everything above 7 or 8 solar masses produces neutron stars, except the things that produce black holes. And where the dividing line is a question for Evan O'Connor and others. But we don't actually know which stars produce neutron stars and which stars produce black holes.
What's the dotted line?
Sorry?
What's the dotted line?
I don't know. I don't know. I think it's a model. But I don't know whose. Stars with masses larger than 2 solar masses are not stars. Stars with masses above 2 solar masses are almost all binaries. Okay? This is the binary fraction with companions, as a function of mass, 0-age main sequence mass. O stars and B stars and A stars, which are the stars that we're particularly concerned with because we're interested in things that produce massive white dwarfs and things that produce neutron stars, are all binaries. All, I use the word roughly here, but let's say over 60% or 70% binaries. And very importantly, if O stars were sometimes in binaries with K stars, you would never know it. Okay? Because O stars totally dominate the light of the system. So this is why these are phrased as lower limits here. Because you observe O stars with O star buddies, and you observe B stars with B star buddies, but it's very hard to observe an O star with an F star buddy, because O stars are bright. So first, we're interested in intermediate mass and massive stars. Secondly, those stars are not stars. They're binaries. Third, binaries are not binaries. Okay? Basically, all close binaries that you see on the sky are triple systems. So imagine you go and you look at a bunch of stars, they're binaries, and you make a plot of the incidence of a tertiary as a function of the period of the binary. Then here you have a fraction of systems that are triples versus the period of the inner binary. And when you're talking about close binaries, inside of about 5 days, roughly 75% of those systems are actually triple systems. Okay? So stars are not stars, and close binaries are not binaries. They're actually triple systems. The overall triple fraction is about 10%. You go out and you look at a stellar system on the sky, 10% of the time it's triple. Is the triple fraction well known for massive stars? No, for the same reason that if you have 2 O stars with a tertiary that's a G star, you'll never know it. Okay? So we don't know much about the triple fraction of O stars and B stars, but we do know that multiplicity, generally speaking, that is binarity, is a strong function of mass. Here's a hierarchical triple system, just sketched. I'm going to say this a few times, so I thought I'd just put up a sketch. You know, M0 and M1, these are the two inner binary components. They might be of 1 solar mass or 10 solar masses or something. The outer tertiary is 1 solar mass. The inner separation might be an AU, the outer separation 50 AU. The eccentricities here, I've just put, I don't know, 0.1. And the inclination, the mutual inclination is key, is 85 degrees. I didn't draw it exactly 85 degrees, but you can imagine 85-degree mutual inclination. Those are the basic parameters that determine the dynamics of the problem. And if you haven't heard many talks on Kozai oscillations, then you might just naively think that the inner binary just orbits around, and the outer tertiary just orbits around, and that's it. If you have heard of Kozai-Litoff oscillations, then you know that that's not true. If the inclination of the outer orbit, that I, is larger than 39.2 degrees, then what happens is you set up a resonance, basically, and you get oscillations in the orbital elements of the inner binary. So what happens is that the inclination of the inner orbit, so here's the inner orbit, its angular momentum is maybe like this, okay? And the outer orbit, the tertiary, it's going like this, its angular momentum is like this. Okay, so you have the inner binary angular momentum, the outer binary angular momentum. And what happens is the inner binary angular momentum goes through periodic excursions like this. Okay, and as it does, the outer tertiary's orbit, the plane actually changes slightly, so such as to conserve the z component of angular momentum, I think. And then what happens is that happens on a certain long time scale. For example, 40 kiloyears, 40,000 years, for a 1 AU binary of solar mass, solar mass, solar mass, and with A2 over A1 of 50. So 1 AU, 50 AU. Okay? And what happens is that as this inner binary its orbit changes like this, it goes to very high eccentricity. It has to, again, from angular momentum conservation. Okay? And the maximum eccentricity is just given by this expression in certain limit, under certain approximations, which I won't get into just yet. Yeah?
So this 39.2 is completely mass independent?
No, it's not completely mass independent. Because at octuple order, this expression is not quite right at octuple order when everything is finite mass. Wait a minute, you're asking about the maximum eccentricity? The maximum eccentricity, or the critical angle. The critical angle, I think, does depend on the masses, if all the masses are equal body, and if all the eccentricities are non-zero. But I also think it's around this 39.2 degrees. It's very close to that. This is a good working approximation. Is that, okay? The Kozai time depends on the masses. This maximum eccentricity doesn't really depend on the masses. Certainly at this order it doesn't. Okay? So the system, the inner binary, will be driven to very high eccentricity. The question is, on what time scale? If your tertiary is a dust grain on the other side of the universe, then it takes forever for that system to go through one Kozai oscillation. Okay? But if it has finite mass, M2 is solar mass, and if the ratio of A2 to A1 is some reasonable number, then it happens in a time scale that's short compared to the evolutionary time scale of the star, but long compared to orbital time, which is less than a year for the system. All right, so the question of why did that plot of Tocqueville et al., why are all the close binaries in triple systems? Why, when you look at close binaries, do you always find that they're in a triple system? The basic explanation that emerges from some combination of the papers here is that all of the close binaries used to be farther away binaries, but what happens is they have a triple system, a tertiary at high inclination. They were driven to high eccentricity, and as they were driven to high eccentricity, they they had a close pericenter passages with their companion, and every time you have a close pericenter passage, you have tides that are raised. This is first said by Mazet and Shaham, I think, in 1979. And what that does is you can take energy out of the orbit. So what you can have is Kozai cycles acting in concert with tidal friction. And you could take a semi-major axis that was like this, and you could shrink it down to a semi-major axis of a few days. And so when you're selecting close binaries, you're actually selecting the triple systems that were affected by Kozai. And Yenshin and Norm worked on this in the context of planets, and so did Fabricki and Tremaine, and Eggleton and Kiseleva. Eggleton applied some of these same ideas. All right. So if all massive stars are multiple and all closed binaries are triples, and these are all affected by Kozai, are the white dwarfs and neutron stars that are produced in these systems also affected by Kozai? Well, the answer is probably yes. And if so, how? And I'm not going to be able to give you a complete answer to this question because, frankly, the parameter space is gigantic and there are a lot of things we don't know. What I'm going to do is highlight a few specific problems that I think might be of interest and where Kozai probably plays an important role. And I'm going to start with talking about 1A supernovae. And specifically, I'm going to talk about the conjecture, I would say, that the rare binaries that produce white dwarfs that lead to 1A supernovae are not binaries at all. Maybe they're all triple systems, every single one of them. Okay. So you want to make a 1A supernova, a beautiful 1A supernova like the first slide of my talk where you see these 1As exploding in galaxies. Maybe you need double white dwarfs. Maybe you need those white dwarfs to merge together for them to be super Chandrasekhar and then to explode. Maybe those are all triple systems. If so, how would they be affected? Again, I'd like to give you a complete answer, but I think I won't be able to. So in order to explain some interesting things about this conjecture, I'll first start with another little bit of the census. Okay? So 1A supernovae. Suppose we want to make super Chandrasekhar white dwarf binaries. That means we need each white dwarf to be larger than about 0.7 solar masses. That means that we need main sequence stars above about 2.5 solar masses. If you just look at the census of all 2.5 to 8 solar mass stars, you need about 2% of them, 2%, to become 1A supernova. All right, this number 2% decreases if you believe that sub-Chandrasekhar mass white dwarf binaries can produce 1A. Okay, it's been suggested by your colleague. Right, who's missing right now. So in what way are these stars that produce white dwarf binaries intrinsically rare? Well, you only want 2% of these stars to produce 1As. How are you going to do that? Well, something interesting, some different property there must be about these binaries that produces 1A supernovae, since the actual incidence of binary is very high, larger than 50%. Okay? And the typical story goes like this. Here's the typical story. This is Eben and Tudikov, 1984 and 1985. You start with two, let's say 5 to 8 solar mass stars. Their initial separations are close. There may be 10 to 1,000 R sun. What happens to them? Well, the primary expands off the main sequence. Common envelope evolution ensues. You're left with a helium star and the secondary. The secondary then evolves. There's a second epoch of common envelope evolution. There's a total reduction in the semi-major axis as a factor of somewhere between 10 and 1,000. So you start with these stars out here at 1,000 stellar radii. They go through common envelope evolution, then common envelope evolution, and they're brought together to some very small value. The compact CO white dwarf binary you end up with 1 solar mass and 1 solar mass white dwarfs, would be some semi-major axis of 0.1 to 10 R sun. And you ask, how many of those can merge in a Hubble time? How many of those can merge to produce our 1As in a Hubble time? Well, you need the semi-major axis to be inside about 3 stellar radii for things to merge on 1 Hubble time. If you want T gravity wave to be less than T Hubble, you need the semi-major axis to be less than 3 stellar radii. And the evolution, this whole thing, depends on common envelope evolution, which if you've ever gone into the literature is very uncertain. And nevertheless, T-gravity wave, time to radiate and to in-spiral is about 10 to the 10 years for about 0.015 AU for all stellar mass things. So the answer to the question, why do only 2% of the stars produce 1As, could be that only 2% of the stars are born with companions that are in the semi-major axis range you need in order to eventually produce a tight enough white dwarf binary to merge. Okay? Now there are a couple problems with this scenario. The first one, this is work by Reuter et al. 2009, but there are many other studies. This is work by Reuter et al. Doing population synthesis of binaries. And what they find is they plot the supernova 1A rate. This is blue. These are double degenerate systems that I've been talking about. White dwarf plus white dwarf systems. And you get some fractional rate, supernova 1As per year in a given stellar population as a function of time. Here, 5 gig years, 10 gig years, the age of the universe, and then 15 gig years. Okay? And then here, you actually have the observed rate, which is this line. And then you have your double degenerate systems plotted as that rate. And a couple of things you'll notice right away is, first of all, it seems like the rate is less than observed. by some factor, maybe not by much. Maybe you'd say that's perfectly fine for astrophysical precision, and I would mostly agree with you. You would also see that the rate is a little bit lacking here by some orders of magnitude. So the first problem is that, well, the rates might be a little bit low, the predicted rates. Okay. Problem 2 actually focuses on that early time part right here. Is that there's a component of type 1a supernovae that observed to be prompt. These are called prompt 1a supernovae. A component, some fraction of 1a supernovae, occurs in star-forming galaxies, and they're thought to be produced less than a gigayear after star formation. So imagine you look at a galaxy, there's a burst of star formation. When's the first 1a? The first 1a is actually about 100 megayears to about half a gigayear after that burst of star formation. And this is work by Scanapico and Dilston, but also by Minucci, and then various statistical studies have been made on by comparing the type 1a rate to the star formation rate. Now the thing is that massive CO cores are built by stars of about 5 solar masses, with main sequence lifetimes of about 10 to the 8 years. And so you need them to merge, these white dwarfs to merge essentially immediately after birth. And most answers to this question, how do you get that to happen, would be common envelope evolution. Somehow common envelope evolution moves these things in close where they can merge super rapidly. Not on a time scale of 10 to the 10 years, but on a time scale of 10 to the 8 years. And the question is, are there sufficiently many Chandrasekhar mass binaries with p less than 8 hours to actually produce the supernovae in significantly less than a Hubble time? If so, then you should see these binaries. So problem 1 is generally that the rates are less than observed. Problem 2 is that there's a prompt component that needs to happen very fast. And problem 3 is that there aren't any progenitor systems found so far. I put a twiddle by no progenitor systems found because this is a moving target. First of all, it changes month to month because these guys, especially Killich and Brown and Wally and a few other people, are busy trying to find white dwarf systems that will actually merge in less than a Hubble time. So what am I showing you here is the total mass of a binary, total mass of a white dwarf binary. These are total masses of white dwarf binary systems, and this is a function of their period. And this is the line that separates T gravity wave is equal to T Hubble. And the statement that no progenitor systems have been found is a statement that there's nothing here. And I put a twiddle on the no because, first of all, it's a moving target. Second of all, there are arrows up because only minimum masses on some of these aren't known because of inclination. So, but roughly speaking, there are these 3 problems. Rates too low, required prompt component may be too prompt, and there's not enough progenitor systems found. And the question is, are triples part of the solution? So let me discuss that. Triple scenario would be quite complex, exactly what would be going on. But again, you start with a binary of 5 solar mass stars with separation, 10 to 1,000 our sun. The tertiary component is sitting out there at maybe 3 to 100 times the inner separation. Okay? If the inner binary components, M0 and M1, are more massive than M2, then you would go through your 2 common envelope phases. A1 decreases, A2 actually would increase because of mass loss. Either the white dwarf merger happens, or M2 evolves off the main system, main sequence. It could even engulf. This would be scary. But the white dwarf binary could be engulfed by the tertiary, in like a triple common envelope evolution. But in the end, you'd be left with a hierarchical white dwarf binary with a main sequence companion, or a triple white dwarf. If M0 and M1 were actually less than the tertiary mass, then M2 would evolve first. You could, in fact, then engulf the inner binary. You could have another common envelope evolution, and so on. And this is all extremely uncertain, and as far as I know, nobody's modeled that. And maybe people in this room are thinking about modeling these evolutionary sequences. But this is kind of what I have in mind. 5 solar masses, and then, say, 1 solar mass tertiary. What happens? I'm not in a position to do this whole evolutionary calculation, so I'm going to show you the results of some simplified calculation. So here we go back to our hierarchical triple system. Now I want you to imagine that these 2 components are both white dwarfs, and the tertiary sitting out there is maybe a 1 solar mass main sequence star or a white dwarf. Let's put the initial separation be 0.1 AU. So the gravity wave time is 10 to the 13 years. It's 100 times the age of the universe. 100 times the age of the universe. And we make the semi-major axis of the outer guy maybe 2 or 20 or 50 AU. We give low eccentricities, we make the inclination 85 degrees, and we compute. First thing we do is make an estimate, and the estimate goes like this. The gravity wave merger time I've been showing you for the last few slides is proportional to the semi-major axis to the fourth power. Okay? But I left it out for pedagogical purposes, partially to kind of lie, so that now it would be more dramatic. Okay? The gravity wave merger time has an eccentricity dependence that's very strong. So the gravity wave merger time depends very strongly on the semi-major axis, but also depends very strongly on E1, the eccentricity. Well, if the Kozai oscillations are going to periodically push you to a maximum eccentricity that's 1 minus cosine of the inclination squared, then you could just substitute in here. Okay? Just substitute this into that. And then make a correction for the fact that only part of the time is spent at high eccentricity. Because sometimes it's high eccentricity, sometimes low, high, low, as the binary goes like this. And every time it goes to high eccentricity, it burns its fuel, its gravity wave, in gravity waves. You correct that, and you get that the merger time goes like cosine I to the 6th power. Cosine I to the 6th power. So remember, the inclination of 90 degrees is cosine I of 0. And so that would say the merger time would be instantaneous. If the inclination is 85 degrees, as I was suggesting, that's cosine of 0.1, and 0.1 to the 6th power is 10 to the minus 6. So we know that this is going to be a very strong factor. Yes?
You're going a little fast.
Okay.
Let's take this inner binary. Suppose they're eventually going to form two white quarks.
Yep.
And they have this triple companion.
Yep.
Which is essentially evolving on this fast time scale.
Yep.
So they're undergoing the Kozai oscillations.
Yep.
So won't, in practice, this type of setup force you to have a collision between those two inner stars when one of them is in a subgiant branch? You know, it's big enough to eat the other one, but it hasn't fully evolved in this relatively brief, full-fledged red giant type of phase.
Yeah, so the picture I would have is the following. The picture I would have is that you have the binary. It's being forced by Kozai oscillations to high eccentricity. But the system is evolving, and as it's evolving, it will eventually go into tidal contact. And basically, then the Kozai oscillations will essentially shut off. When you're in tidal contact, Kozai can't generally compete with tides. And so the system will evolve as kind of a isolated, tidally interacting binary for some period of time. Okay? And then it will eventually become, and this is where I am waving my hands right now because I don't have the full calculation, I'm not in a position to do the full calculation. You're going to end up with a white dwarf binary.
Maybe.
Yeah, maybe not.
I would worry that you would just get one complete merger.
A stellar merger.
Well, I mean,
You want a stellar merger while they're, you mean bring them to contact and then have them merge while they're stars? Before they're contact
I mean,
objects?
if you have a main sequence, a star that's still a main sequence star interacting with a subgiant, what happens? I mean, it's, the envelope isn't very extended, right? I mean, there's this usual argument that you change the position of the companion, and when you change the binary to the companion, it pours largely the binding energy of the envelope before the envelope goes away, right?
That's right.
But if it's relatively compact subgiant star, it's not particularly the argument lets you eject the envelope. In that case, if it doesn't eject, you get a merger.
Possibly, yeah. You can possibly flip all those stages, all the pieces that you just said were right.
Actually, I would say that it's not going to happen because we have large stars that cause that.
Physically, large stars interact tidally, and basically you advance periastron via tides, and that's bad for Kozai. So Kozai is quite delicate, and like I said, I don't have a complete evolutionary sequence, but the picture I have in mind is that Kozai basically shuts off for some period of time while the things are tidally interacting, and then when they're rocks, Kozai acts again. Yeah?
That inspection neglects the effect of relativistic precession in the inner binary, right?
That's right.
And that would quench Kozai cycles.
Yes, that's
How
right.
does that affect the 6th power of
Yeah. So the question, as Fabio knows as well, anything that advances periastron, not just tides, but for example general relativity, kills Kozai. And so this is the simplest possible estimate that you can make, which I think is a decent rule of thumb. But in anticipation of my next slide, I prompted him to ask that question. General relativistic precession does detune Kozai, and in in fact, the general relativistic precession time is pretty short for the type of binaries we're talking about, and it also has an eccentricity dependence. So as the thing is driven to high eccentricity, GR precession time can be shorter than the Kozai time, and you detune Kozai. So that's why you need to solve the whole system. So these are the equations of Blaes and Socrates. So one day you just pour yourself a big cup of coffee and you sit down in the silence of your room, maybe listening, in my case, to some Rachmaninoff, and you very carefully code this up. And then you get something wrong, and it's obviously wrong. And anyway.
Well, first you reduce it, then you code it.
Well, what's shocking is that there is no error in this. This is right.
Oh, no, Omer is the first off.
There you go. Okay. This turns out to be exactly right as far as I can tell. Okay. Yes.
What about formation? Like, do we know from star formation models at least, like whether wouldn't you be more likely to form all three in the same plane?
So this is it's a great question. So the question is, the solar system, everything's coplanar, angular momentum's in this direction, nothing should ever be high inclination, and when you see models of binary stars forming in very massive disks, you might expect if a triple was going to form, it would just form a larger semi-major axis. It's a great question. There are a couple of answers. So first of all, the triple formation is not understood. Triple star formation is not understood. Out of these simulations by, must be Bate and Bonnell probably, and also some simulations by Krumholtz et al. Of cluster formation, they do get triples. And most of those are weird exchange interactions that happen in some in the dense environment. In the tertiaries, as far as I understand it, that can be at whatever inclination.
So do you need this dense environment to go away for Kozai to work, right? Because if you just have the spherical dimensions.
So also a good question. The triple system I'm imagining here is now in dynamical isolation. If you do put a triple system into an environment like a globular cluster, where the tertiary is going to be knocked around, then any number of horrible things can happen. Okay.
So the answer is observational.
Observationally, triples exist,
And
and
the inclination is
unknown.
no. In many cases, it's known, and it's
Really?
Yeah, well, it does.
Okay, dozens.
And it's looks like it's really random if you're all beyond a certain measure.
And remember that the triple systems that are not the binaries that are not binaries, those via this explanation I gave you in the beginning, the inclination of the tertiary would have had to have been at fairly high to bring them to time apart.
And the other answer to your question is yes, every star you've seen in the field was in a dense environment in the past.
Right, and that would be a worry. But then, the Kozai time might be tens of thousands of years, and if 100 of those timescales, or maybe 1,000, star clusters have a whole range of disruption timescales from 10 to the 5 to 10 to 5 years to infinity. Yes.
Okay, so there's also the part where gravitational wave emission circularizes your binary.
That's right.
Is how that interacts with Kozai.
Yeah, so that's here. So this is the ADT from general relativity, so shrinking of the semi-major axis. This is dGdt, so how the argument of periastron advances as a result of the Kozai oscillations and as a result of GR. That's this term. Okay. Then you have the eccentricity. Here, this is the general relativistic terms. These are the Kozai terms. dAdt is easy. Go that rapidly. That's the outer tertiary semi-major axis is not changing. And then you have the tertiary's argument of periastron, its eccentricity, and then the total angular momentum of the system. So that is going to come into play, and this is what the evolution looks like. So you start with a binary, let's say, of 0.8 plus a 0.6, suggestively sums to 1.4 solar masses, with a 1 solar mass tertiary, okay? And then you take your initial conditions are low eccentricity, the semi-major axis is 0.05 AU, and your guys should merge in 3 by 10 to the 12 years, so 300 Hubble times. And then you just look at this plot. For the moment, ignore the left plot. This is time, 10 to the 7, 10 to the 8, 10 to the 9 years. This is the eccentricity going from low to high, to low to high, to low to high, to low to high. And here I've downsampled this curve by a factor of 20, so you can actually see a little bit of white, and also so it doesn't make for such a big figure. But basically it goes up and down. Each one of these up and downs is a Kozai cycle. You see those Kozai cycles are here, up and down. So this is 1 year, 10 years, 100 years. And then this is the whole evolution. And the eccentricity envelope here, right, goes from eccentricity high down to eccentricity 0. And the semi-major axis goes from high value down to 0. Okay, and the system merges.
Are
Yes?
tides important?
Sorry?
Tides are important.
Not for this setup, no.
But
Tides are never important. I mean, there would be important when the white dwarfs come to contact.
Even at the highest eccentricity,
Yeah.
amount.
Not for this one. Not for 85 degrees. It's close, but not for 85. So what I can do is I can use a sort of semi-analytic method. Actually, there should be a citation here because this should be Wen 2003. So Wen in 2003 developed a semi-analytic method which can be applied to this, and you can survey a huge swath of parameter space. So this is the swath of parameter space. For the same system I just showed you, rather than doing the integrations for every single one, I'm just going to survey all of parameter space. And you have to trust me that for certain approximations, this works extremely well. And so what am I plotting? So here's cosine of the inclination. This is 90 degrees. You know, way over here is coplanar. Way over here is retrograde and coplanar, right? Because you can have the interbinary like this and the tertiary coplanar in the opposite direction, okay? And then what you do is you plot as a function of A1. So here's 0.01 AU, 0.1 AU, 1 AU, and 10 AU. You put your white dwarfs at 0.01 AU, and the merger time is the Hubble time, 10 to the 10 years. You put your white dwarfs at 1 AU, and the merger time is 10 to the 18 years. So that's 1,000,000 Hubble times. 100 million Hubble times. Okay? 10 to the 20, and so on. This is normal gravity waves if you were in circular orbit. And then you put a tertiary at some multiple of the inner semi-major axis, like 40. Okay. You assume low eccentricities, and you compute the merger time. And the merger time is less than T Hubble if you're inside this black curve, All this region, the merger time is larger than the Hubble time, and in many cases, many, many, many times larger than the Hubble time. But in here, it's less than the Hubble time. In here, less than 10 times the 10th the Hubble time, 100th the Hubble time, 1,000th the Hubble time. So these guys in white right here merge in 10 to the 7 years. 10 to the 7 years. So the relative speed up is very, very, very large. Okay, yes?
So this is all for the 0.8, 0.6 solar mass boundary. Meaning 1.4 solar masses doesn't make the supernova mergers, as we know.
That's right.
You need 0.9 mergers.
Yep.
How long that makes?
Basically nothing would change if it was 0.9 plus
Okay.
0.9,
So the
0.8
mass,
plus 0.8.
the mass and the mass ratios don't really matter.
Not unless those mass ratios differ by more than a factor of 2, then I would stop saying what I'm saying right now. But as long as the masses are within a factor of 2 of each other, and as long as the tertiary is about a solar mass, nothing here changes. If the tertiary is a Jupiter mass object, then it wouldn't. Okay, then I would change again.
What happens if you have A2 array with 1 or 400?
400, it shuts off. The whole mechanism stops at 400.
So can you explain in a little bit more detail? Because that is a crucial piece of this, how it depends on the
It is a crucial piece. Basically, the Kozai time becomes very, very long as the cube of the ratio. Okay? And so if all of a sudden I put A2 over A1 to be 500 or 600, then a single Kozai time is approximating, you know, a fraction of a Hubble time, and I'm out of business. Okay? That's why. Because it goes as the cube. So I quickly run out of, I don't have enough Kozai times to fit into the time I want to work.
So here you're dealing with a binary less than 10 to 11 centimeters or so apart, a few times 10 to 11 centimeters apart.
Well, here is at let's say 0.1 AU. Okay, so that's 10 to 12 centimeters apart.
Okay.
So that's 0.1 AU, and the tertiary would be a 4 AU. 1 AU, 40 AU.
Yeah.
Okay?
How do you slow down the merger?
How do you slow down the merger?
Yeah.
What do you mean?
Because outside these
Outside these bands?
Yeah.
It's slower because the cosine of the inclination is low, and the Kozai time is long. And so the max of eccentricity is low. It doesn't get as high in eccentricity. And the number of Kozai times or the Kozai time is longer. And the thing basically essentially never merges.
But you said it's longer than assuming just circular gravitational waves.
No, it would be the value for circular gravitational waves in that case. Essentially.
Oh, sorry.
There would be a small correction, but the eccentricity would be small.
Yeah, I was confusing them all the time.
Okay. So if you want prompt mergers, this is one way to go. If you want prompt 1A supernovae, you can do it this way, because you can drive gravitational mergers by gravity waves like that. One thing you could do is you go back to this plot, and one way to graphically illustrate this is to put down lines that correspond to 1,000 Hubble times, 10 to the 6 Hubble times, 10 to the 9 Hubble times. And then I can say, well, give me a tertiary, and let me put the tertiary of one solar mass anywhere I like, let's say at an inclination of 70 degrees. A one solar mass tertiary at 70 degrees, okay, gives me a contour in the space that would say all of these objects, if they had a tertiary, at 70 degrees, would merge in one Hubble time. All of these objects, if they had a tertiary of 80 degrees, would merge in one Hubble time. 85 degrees, one Hubble time. 89 degrees, one Hubble time. 90 degrees, one Hubble time. Okay? That is, if you allow me the freedom to place a tertiary at 90 degrees inclination, how much does this parameter space open up to you? It opens up all the way out to here. That is, you could find a white dwarf system here. It would be extremely short-lived. It would be extremely highly eccentric. It would be possible to find one here, and it would merge in less than a Hubble time, even though your naive estimate for circular orbits would be something like 10 to the 8 Hubble times or something. Okay? Now, I've given myself a lot of freedom here because I've taken a one solar mass tertiary, and I've allowed myself to put it anywhere at any distance from the semi-major axis of the inner God. And these little numbers, if you're interested, are the period in years of that body. So for example, here's 254-year tertiary at 89 degrees would cause any system right here to merge in less than a Hubble time. And so that's what this diagram shows you, is how much bigger the parameter space gets once you allow yourself a tertiary.
So talk a little back to this diagram. So what, So what do you think of the astrophysically relevant gravity space in this two-dimensional world? So given boundary evolutions, given the fact that there was Kozai in the main sequence, Kozai in hybridization main sequence.
Yeah. Honestly, normal binary evolution to do anything is everything less than 1 AU. So if you want your system to be brought into, let's say, for them to undergo any binary evolution, it would be inside an AU or two out here. Okay.
So by the end, the common envelope would be much tighter.
They would be tighter, but how much tighter? I don't know, a factor of 10 to 100. So they could move down here, they could move down to here. And the tertiary could be at some inclination. I don't know what the tertiary's inclination is going to be. If it's brought to tidal contact and the whole thing circularizes, it could shut itself off, because the inclination of the tertiary could be actually pretty low. Okay? Could be pretty low.
So I was wondering whether the 90-degree neighborhood is excluded because
of the previous evolution?
Due to the previous.
I think it could be, but I think that is left to, that is work for people, either in this room or me or my graduate students. We have to figure out what triple star evolution looks like. That means we need to take binary star evolution models and fold them with Kozai. And I'll give you a reason, hopefully I'll get to it, a reason why it's actually much more complicated than this whole picture suggests. If it was just this whole picture, I think it would be, I don't want to say easy, it would be easier, but things get awful pretty fast. Okay. All right, so summary would just be that if the triples were uniformly distributed in Kozai, if they were, and I agree they might not be, and systems were uniformly distributed in log A, then what would you say? Well, the speed up time relative to circular orbits is a factor of 100 for 20 to 50% of systems. So everything you know about rates from these population synthesis studies would be totally destroyed, I think, because 50% of systems would merge a factor of 100 faster than we think they should. And it would be a factor of 10 to the 6 for about 10% of systems. Okay? And those are very big numbers. Okay? And that's why I'm optimistic, but cautiously optimistic, because these assumptions are large. Uniforming Kozai and uniforming log A, given the preceding binary evolution, which has yet to be done. And since 10% of solar type systems are triples, about 1 to 5% of all systems should be strongly affected by Kozai. And this is of order the rate of supernovae, and hence, it's at least relevant. It's not the case that the fraction of triples is many orders of magnitude smaller than the fraction of stars that become supernovae. They're comparable, or actually the number will be larger. So the problems that I started with, which that the rates are not high enough, and especially early times, you need this prompt component, this would solve that problem very easily. Okay, the answer is that Kozai can work for prompt white dwarf mergers. Now, I gave you another problem, which is that there are no progenitors seen, and you would say, hey, the same problem with your system. When have you ever seen a compact white dwarf binary on a highly eccentric orbit with a tertiary? And I'll give you the answer to that after I answer Lynn's question. Yes?
The observed rate is like a prompt plus a longer.
Yeah, the observed rate, yes, can be written that way.
So then, does your picture give like two components, or does it just give a smooth background that's faster at shorter time?
It's a great question. Let's just do the case of uniformly distributed in Kozai. Uniformly distributed in Kozai, this is all prompt. And everything at smaller Kozai, or larger Kozai, sorry, absolute value, is basically never affected by Kozai and lasts forever. And so I wouldn't say there are two components. There's one that happens instantaneously, and there's another that takes forever. That takes as long as a normal binary that's totally unaffected by Kozai. Because if I put the tertiary at 10 degrees inclination, not a damn thing happens.
So your mechanism explains the prompt stuff, and then there's another mechanism.
Then there would be a long tail. It's just that I haven't done any of the population synthesis with real stellar evolution to give you an actual model.
But does your picture explain both the prompt and the
It would explain the extended component, because any binaries that stayed far apart and had a tertiary at 0 degrees inclination would take a Hubble time to evolve. So yes, it would explain that. So it would do both. Because it's just a steep function of cosine. All right, now I said not enough progenitor systems found, and you would say, well, none of your progenitor systems are found either. This is a long slide. I want to emphasize a couple of specific points that I really want you to hear. Okay? The first one, so first the strong triple conjecture, which is a straw man, okay, is that all tight white dwarf binaries are or were in triple systems. That's a straw man because the white dwarf systems I've been showing you are not in triple systems as far as we know. Objection number one, none of the white dwarf binaries seen are highly eccentric. And none of them seem to have triples. This is the thing I want you to understand. Whenever anybody has gone to search for white dwarfs, they're color selected. White dwarfs are color selected. You go and look at SDSS, you look for blue things. You select the blue things, and it's a white dwarf. But now imagine you have two white dwarfs and an A star. Are you going to see the white dwarfs? No. Two white dwarfs and a G star. Are you going to see it? Well, maybe if you cross-correlated SDSS with Galax and looked for a UV excess, but even then it would be low mass white dwarfs, okay, with a G star. The important thing is that white dwarfs are dim, and you're selecting on color, okay? So the fact that all of those white dwarf systems have been discovered by color selection and none of them have a tertiary is exactly what you would expect.
Wait a minute.
If the tertiary is a main sequence star.
If I look at G stars,
Yep.
then you're considering, say, a system where you have a separation to the chemical centimeters with two white dwarfs, and the companion is a
50 AUA, 20 AUA,
well,
Not
several AU.
You don't see anything.
And if I have two white dwarfs
Yep.
and orbiting a G star, several AU,
Yep.
I'm going to get some really strong people.
You're going to get RV.
Yes.
So you could do a blind RV study,
Yes.
and you could look for RV, right, where the companion is missing, and the companion is...
Years.
Sorry?
Timescales of years.
Many years.
Yeah. So you're not going to do that.
I know, it's awful.
No,
Okay.
look at doing Gaia.
Sorry?
Gaia.
Gaia, so you could do it astrometrically, okay? You could do that. You could do other things. You
Wait a
could...
minute. You have a triple system
Yeah.
with two of the order of solar mass things moving around each other.
You won't see the spectrum from like North.
Wait.
He's asking about RV on the G-star.
Reflex.
It's not going to G-star, but it takes
You'll
seven.
get, wait. You'll get some component of the RV due to the binary motion of the white dwarf.
Oh, just from the motion of the white dwarf.
Yeah.
So Okay, so you could calculate that. All right, I haven't calculated that. You could calculate it. Would it be large? I don't know. Can I move on? This is actually a long slide. The main thing I want to point out to you, and this is important, is that white dwarf surveys are color selective. So that itself is not proof that these things don't exist.
But shouldn't most likely companion will be brown dwarf rather than an A star or G star?
I don't think we know that. I don't think we know the mass distribution of
If they are
associations.
randomly coupled, yes.
I mean, if you do 2 draws from an IMF, there are going to be plenty of times, right? You want to draw an IMF for the primary, draw a P of Q for the secondary, draw another IMF from the other, from the tertiary. You won't, I mean, by number, yes, you would be
But
favored.
those have been excluded.
Sorry?
Those kind of population has been excluded.
No. And so all right. So quickly, how would you want to see a white dwarf? If you want to see a white dwarf photometrically, you look for some wimpy buddy. So let's not worry about brown dwarfs for the moment. Let's do M stars.
Yeah, right.
Okay. You take all of SDSS, you make a color diagram, and there's a stellar locus, there are quasars and various things, and there's a huge band of white dwarf M star binaries because white dwarf M stars have crazy SEDs because they peak in the blue and they peak in the red. And they're easy to find in color space. You select those, and those could be white dwarf binaries with an M star tertiary. So then what you would do is you would do something like what the Dennis and Mullally and Lupton are doing on Sloan, and anyway, there are various things you can do to find those systems. Yes, it can be done. It needs to be looked at. Emails have been sent. I want to mention an implication of this. Kozai induces strong eccentricity oscillation. That leads to smaller T-merge. That's what I tried to show you. Bigger gravity wave luminosity and higher gravity wave frequency. Normally when gravity waves are emitted, they're emitted at omega multiple to omega. And when you go for high eccentricity, you can write the peak of the gravity wave signal as 1 over the eccentricity squared to the 3/2. And that looks like 1 over cos I cubed. So for the same system I showed you before, the eccentricity starts low, high, low, high, low, high, low, high, low. And every time it goes through a high eccentricity excursion, it emits gravity waves in a few millihertz band. So this normal white dwarf binary that starts at low eccentricity emits most of its gravity waves at 10 to the minus 2 millihertz, but then it also emits a significant amount of power at 2 millihertz. Okay, and that's interesting for people who are interested in LISA and LISA-like experiments, because this is a lot of time. There's a lot of time here spent at high eccentricity emitting gravity waves. This will change your assumption about the gravity wave background, because the usual assumption is that all white dwarf binaries are circular because of common envelope evolution. It will also change what you're looking for when you go try to do template matching or something like that, because your individual system is going to sweep through periastron and it's going to fire a pulse of gravity waves at you, and it's never to be seen again, or at least not for a long time. Okay? So that's an implication that, anyway, people in this audience might be interested in. Okay? I can also do the same kind of map I did before. Same map, this is A1, this is cos I, except now I can color code by frequency of gravity wave emitted. The systems that are close to cosine of 90 degrees, cosine of 0, emit a lot of gravity waves in the sort of 100 millihertz range. Okay? And systems way out here are more like 0.1 to 1 millihertz. Now, Fabio's original question was, what about tides? And actually, there's a region right here that's going to be strongly affected by tides. And you're actually going to get a stronger white dwarf interaction. We started 10 minutes past the hour, is that right?
Do you get any systems that have still high eccentricities in the LIGO band?
That would have high eccentricity in the LIGO band? I mean, not that wouldn't be affected by tides, right? Your minimum time scale is going to be of order 1 dynamical time for the white dwarf, and that's of order, hertz, and that's going to be below LIGO band, roughly. So there's a recent discovery by Kurtzendorf et al. Wolfgang's right here, of Tycho B, which is a very, very peculiar star. It is Fe over H minus 1 A star, sitting in within 5 arc seconds of the center of Tycho, the supernova lemon. So you know the story, Tycho's walking home, it's 1572, he looks up, oh, a new star, and it's the Tycho supernova lemon that we see today. Now I've been looking for proof that Kozai oscillations or multiplicity might be important in type 1a supernova explosions. And this gives me an opportunity to say something that might be slightly flaky, but it's still very interesting. Okay? And it's this. There are no -1 A stars in the galaxy. Basically. Why? Because -1 is low metallicity compared to solar. Those stars would be in the thick disk or something like that, where they would have formed many gigayears ago, and A stars live for 100 megayears. If you want to find a -1 A star anywhere, well, first of all, you can look at the SMC, okay. But in our galaxy, the only place you see -1 A stars is in globular clusters. And they're blue stragglers. Okay? They're stars that have main sequence lifetimes much shorter than the main sequence turn-off lifetime of the whole cluster. Okay? Those are the only place to find blue stragglers. So when I saw this -1 A star, my first thought was that it's a blue straggler. And blue stragglers are formed in globular clusters, we think, via potentially several mechanisms. But one of the mechanisms that is suggested by Peretz and Fabricki, and is a riff on the Kozai action with tidal friction that I gave you before, is that you could cause the merger of two stars via Kozai. Okay? So now we have this potentially extremely important discovery of basically the only -1 A star in the galaxy, sitting in the center of Tycho. Maybe that was caused by the merger of two K stars. Okay? And that happened about a gigayear ago. What the hell is it doing in the middle of Tycho? Well, one explanation is that it was formerly a quadruple system. Okay? And most people kind of laugh and shake their heads. Okay, it's okay. I can take it. To a quadruple system. Anybody who knows about multiplicity studies knows that people who study multiplicity are crazy. And so some of the people who know that are like, Todd, you're becoming one of those people. I understand, it's okay. So here's the binary of K stars. The two K stars are brought to tidal contact by Kozai with the tertiary, which is now a binary. Okay? At the same time, these two stars that are going to produce the white dwarf, that are going to merge to become this, are turned into white dwarfs. And the two white dwarfs merge on a gigayear timescale. Okay? And that scenario one is that you have a quadruple system formed from the thick disk. That's B plus B. These guys evolve instantaneously, form white dwarf, plus an A star. Then a 1A and an A star, whose light falls in the detector of, high-res, which is analyzed by Wolfgang and then produces law. Okay? That's the idea. Amazingly, quadruple systems are only about a third of triple systems. So the rates would work out for this. There's no fine-tuning as far as rates. There's no fine-tuning as far as time. Nothing at all. The only problem with this, real problem, is that Tycho V has thin disk kinematics, not thick disk kinematics. It doesn't have the kinematics of a 10 gigayear-old K star or A star. Okay? There are other scenarios, but they all require the Kurtzendorf et al. Metallicity to be much closer to solar. If you want chance projection, the chance projection with a solar metallicity A star is 10 to the -2. If you want a -1 A star, it's down by a factor of at least 1,000. So this is a way multiplicity might actually play a role in supernova studies, local supernova studies. Yes?
The K star also has to be very important, is that right?
Yeah, so it would have been born from the thick disk 10 gigayears ago. This would be -1, -1, -1, -1. Okay? That's the picture. The metallicity is 5. Okay? That's the picture. All right. I want to briefly mention other physics and then stop. Okay? So the other physics I want to mention is first tides. For this whole picture, there is a range of cosine I space where the eccentricity is so high that things will come into tidal contact, where those frequencies get very large. You're approaching the, it's literally a white dwarf screaming around, at R peri is equal to R white dwarf, like that. And that's basically this rate. And it would be nice to be able to do this all with tides, and I haven't, but there are people in the room who can. That's all I'll say about that. My picture is that probably the thing tidally circularizes at R is R white dwarf and then merges. But there are very, very interesting things. For example, you might have tidal heating, and tidal heating in a white dwarf can be interesting. Because it might explode. Okay, I'll leave it at that. A lot of interesting things to do with tides.
You can also get them to hit.
Say it again?
You can also get them to hit.
You can actually possibly get collisions. So that is a topic of current research. to actually see if you can get collisions. If you ever wondered whether black hole collisions could happen too, head-on black hole collisions, most people who study gravity, such things would say, oh, the cross-section for that is 0. I don't think the cross-section for that is 0 in a triple system. Fabio and I, anyway, the numerous people here could discuss that. But it's an interesting possibility, because those are not waveforms that LIGO was looking for. All right, I want to give you a significant complication that was that my student Ben Chapi and I put into the mix, okay? Into the mix of all of this kind of tapestry of Kozai-related physics. And it goes like this. Recently, Boaz Katz and collaborators, Lithwick and Nose et al. Showed that when you expand the three-body Hamiltonian to octuple order, not to quadruple order, but to octuple order, in your secular equations, those god-awful things I showed you from Blaes and Socrates, what you find is that you can, the whole dynamics, you know, the little, the thing I was giving you before with the thing, with the thumbs and the orbits, can totally change. So what you can have is your inner binary is doing its normal Kozai thing, normal Kozai, and if this term, epsilon octuple, the strength of the octuple term, which you'll see depends on the ratio of A's, it depends on the outer eccentricity, it depends on the mass difference, the inner orbit can actually flip with respect to the outer orbit, and the eccentricity can dive to 1 minus 10 to the minus 4 or 1 minus 10 to the minus 5. The eccentricity can become super high. Okay? And so those simple formulae I gave you before that were based on the normal Kozai, quadruple order Kozai, are broken if the mass ratio between the inner two binary components is large, and if the eccentricity of the outer body is large. And so we decided, what we did is we said, well, what happens when the primary evolves off the main sequence? Imagine you set up a system that's very distant, and it has a tertiary that's going around, and you have a 7, a 6.5, and a 6 solar mass objects at 10 AU and 250 AU. 10 AU and 250 AU. And the inclination is modest, let's say 60 degrees. On the main sequence time of the 7 and the 6.5, for the main sequence time of the 7 solar mass guy, nothing happens. What happens to the eccentricity is it goes low, high, low, high, low, high, low, high, but nothing happens. They don't interact tidally. It's not very high eccentricity. Nothing's going on. Just minor Kozai modulation, minor Kozai modulation, minor Kozai modulation. And then the 7 solar mass primary evolves into a 1 solar mass white dwarf. And the difference between 7 and 6.5 and 6.5 and 1 is large. And what happens is that the primary evolves off the main sequence, becomes a 1 solar mass white dwarf, and all hell breaks loose. So that's what we're showing in the top panel. The mass goes from 1 to, in normalized units, from 7 down to 1 solar mass. That's right here. And when that happens, all of a sudden this epsilon octuple term gets big, and you excite this thing called the eccentric Kozai mechanism. So here, normal Kozai, normal Kozai, normal Kozai, normal Kozai mass loss, eccentric Kozai mechanism pushes the maximum eccentricity to 1 minus 10 to the minus 4. And this is 2 times the stellar radius of the secondary. Yes?
So do you include the GR effect?
Say it again?
Do you include the GR effect?
No, for this one there's no general relativistic effect, because general relativistic timescales are generally shorter than all the other timescales we care about here, because we're only going to scales of several R sun. Okay, so general relativistic precession does not dominate the Kozai time here. So it's okay that we're not doing general relativity here, as far as I understand. Okay?
Because you weren't doing tides. You put it in quadruple.
No, there's no tides here either. Okay? So the statement is just that. Mass loss induces crazy behavior. These things will come to tidal contact, something will happen. It's for people who have tides in their codes to figure out. Again, I know it's just a matter of writing down some ODs, but I haven't had time to do it. The people in this room have had time to do it. And the point is, all hell breaks loose after mass loss. And you could do the exact same thing for massive stars. Take a massive star, 11 solar masses, 10 solar masses, 10 solar masses. The 11th solar mass goes to a 1.4 solar mass neutron star, and again, all hell breaks loose. So here's normal Kozai oscillations, then the neutron star is born, and then goes diving to the photosphere, basically, of the secondary, which in this case is a 10 solar mass star, and on a timescale that's a fraction of a megayear. What happens with mass transfer? I don't know. What happens after the second supernova? I don't know. What happens with neutron star kicks? I don't know. See related work by Shinajana and Norm for double compact objects. All interesting things to pursue. I don't know what the answer is. I'm going to skip this. What time is it? So what I've tried to do, so some 1As are prompt, but gravitational wave-induced mergers are usually slow for circular orbits. I'd like to speed them up, and you can easily. There are powers of 10 to the 6 lying around in the Kozai mechanism without any fine-tuning, but subject to all the caveats of evolution that we talked about before. 10% of stellar systems are triples. They're ample triples to account for the 1A rate. Ample. Okay? Kozai brings the systems to tidal contact. You wait for the compact objects to form, and then Kozai resumes. The result is that a significant fraction of triple systems, and thus a non-zero fraction of all stars, will be strongly affected by this mechanism. But this depends strongly on the inclination distribution and everything else. It really depends what we like as a census of triples. It would be nice to find a tight A-star binaries with a companion, if there is such a system. Exter et al. Have 2 A-stars in a tight orbit with a white dwarf, a tertiary. Just like the kind of systems that we're imagining here in the midst of its evolution. It would be nice to find K-stars with a blue excess to do these RV searches to actually figure out what is the triple census, what is the incidence of close or eccentric white dwarf binaries with the main sequence companion, but there is literally no data except for serendipitous finds on that. Somebody has to do a systematic study. This thing, this meek I mentioned, is the evolution of systems is made complex by mass loss. You can trigger crazy dynamics with mass loss and mass transfer. Is Tycho B a blue straggler formed via Kozai of another binary that became supernova 1572? If it's really a -1 A star, then you need an exotic explanation. Because there are no such thing in the galaxy. And 5 arc second from the center of the X-ray remnant is something. Okay? I wanted to talk briefly about dynamically formed triples, but I didn't get to it. There's a whole bunch of ongoing work. Since you can guess probably what it is, I'll just leave it up. So thank you very much.
So we'll have time for a couple more questions.
I guess I wasn't sure why you want to focus just only for the prompt. But let's say it also works for the delayed population of supernova 1A.
Yeah.
Weren't there some recent studies showing there were no remnant stars or no companion stars within the supernova 1A remnant?
Yeah.
How would that,
So there are a bunch of studies like the Kurtzendorf et al. Work where they're looking at nearby supernova remnants and they look for companions. And most of those are in the sort of single degenerate picture where you have a star that was right next to the white dwarf, and when it exploded, that star would have flown off with high proper motion, and it might have been ablated, it might have had interesting elements dumped on its surface, and so on. And you basically see in all the cases where you can see, you basically see nothing. The only interesting thing that's seen within any remnant is the Tycho B.
the absence of any main sequence remnant?
Yes.
Would that make it troublesome for this scenario?
So if there was a tertiary that's a G star, I don't think so, because most of the cases you wouldn't even be able to see a G star at the distance of these remnants. That's the first thing. Also, the G star, if it's a tertiary, would have not very interesting kinematics because it's 50 AU away from the thing that exploded. It also wouldn't be ablated, wouldn't be shock heated, and very little abundance would land on it. Okay? The only thing you could do is look for such a star with blue shifted absorption lines from the supernova remnant to know that it's inside the remnant. Do you see what I mean? So that's something that you could do if you could find such a star.
We could just do proper motion.
Well, but the thing is, there's no proper motion because it's 50 AU away from the explosion. There's no, it has no.
It's got the same motion as the supernova.
Oh.
The same radial velocity.
Same radial velocity as the supernova remnant. Usually those things are not determined well enough to be very constraining. So we could have, Wolfgang give us a disposition on that.
The problem with what you're describing here, we don't find anything in these supernova remnants.
Down to what limits in terms of main
So down to S1006, we go to 0.2 solar luminosities in RV studies, and I think 0.5 solar luminosities in stellar parameters, where we actually look at the stellar parameters.
Yeah.
And we do not find anything that looks not like a normal star. In S1006, everything looks like a normal star.
There are normal stars there.
There are normal stars there. There are many normal stars.
How many? 10? There are 1,000.
Not in the center, so we have 80, we have high resolution spectroscopy, we have 80 stars in the center.
They're all normal.
2,000 kilometers per second, like then a movement across.
So you see, you mentioned
from the center.
there are 80 at the center of 1006 that look normal.
Yeah, and they're all
And all
showing.
of those could be the tertiary.
But you've got radial velocity, so
We
again,
have radial velocities.
you have some distance estimate for them.
We have some distance estimates, but the distance estimates are only from log-G determination,
And
which
main
are,
sequence fitting.
the error bars are
And
huge.
do
But
you have error estimates for the supernova?
the supernova distance, yeah. So we have for 1006, we have 2.2 kiloparsecs plus
Right,
minus
so do
0.5.
you proper motion or do
You could at least try to eliminate some of the 80s.
You can eliminate some of them, but the problem is that with the errors that go into these distance measurements, you're going to be very, so unfortunately
But
this,
with Gaia, this would be good.
and it should be worse, and it's much worse, because the tertiary, in many cases, for intermediate mass stars, I would suggest would be a white dwarf, in which case you see nothing at all. So I think that it's very, unfortunately, this scenario has the problem that it doesn't make an obvious prediction that's observable.
The problem is also you have a huge distribution in radial velocities. If you look, for example, at the Blaes like this is like 20 or 30 kilometers per second, 1 sigma.
Right.
And so, like, anything like this can just get lost. You can never disprove that it's there, you can never, well, I mean,
If it was inside the remnant,